Previous videos in this series have gone over the history of the development of thermodynamics and developed the first law and second law in terms of homogeneous systems of perfect gases. In this case, pressure, volume, temperature, and heat were the only variables needed, and the number of moles was ignored because for a homogeneous system, that simply becomes a scalar, where 2 moles give you twice as much energy as 1 mole. Moving forward into the theory of thermodynamics to make it useful and applicable broadly, you have to look at material equilibrium. In this case, the number of moles actually changes. Remembering that reversibility requires holding one variable constant, now, in addition to PV, T, and Q, the number of moles now becomes not only useful, but central. The easiest type of material equilibrium is phase equilibrium, where just generally speaking, let's say 2 phases exists. A single component that can either exist in phase alpha or phase beta that are in equilibrium with each other. At equilibrium, by definition, delta G is going to be 0. The Gibbs free energy defines what is spontaneous and what is not spontaneous. A process is spontaneous going forward if delta G is negative. It's spontaneous going in reverse if delta G is positive. So if the forward and reverse directions are equally probable, you get a delta G of 0. This particular statement has a new aspect added. The superscripted 0 next to G. Anything with a superscripted O next to it is what means it's a process done under what are called standard conditions. The standard conditions mean for each component in the system, you're at 20 degrees C. Each and every gas that may be present in any phase is at 1 atmosphere. And every component in a solution is at 1 molar concentration. So, I have an equilibrium between phases alpha and beta with a standard delta G of 0. Delta, as you recall, is a state function where delta G is G0 final minus G0 initial. In this particular equilibrium, I have a single component, meaning chemically and physically I have one compound, one component that's existing in 2 phases, alpha and beta. Those phases are in the same composition, at the same temperature, at the same volume, and overall the number of moles of this particular compound I have remain constant. The moles are just changing between 2 phases. This requires the introduction of another variable. The Greek letter mu, where mu sub I is something called the chemical potential. Defined, the chemical potential is how the Gibbs free energy changes as I change the number of moles of N at a constant temperature and pressure. Since the chemical potential is related to the Gibbs free energy, for any particular component I, the potential of I is minus S of I dt plus V of I dP. This definition will become important. Essentially, the chemical potential is saying I have a multi-component system. Each one of those components contributes energy. So the entire Gibbs free energy is just the sum of the potential of each component times the change of number of moles of that component. So I have a phase equilibrium between alpha and beta where delta G is equal to 0 That means that the potential of alpha is equal to the potential of beta, or minus S alpha dt plus V alpha dP is equal to minus S beta dt plus V beta dP. I can rearrange this to get a couple of state functions. Minus S alpha plus S beta equals V beta minus V alpha. S beta minus S alpha is the delta S of the transition. V beta minus V alpha is the delta V of the transition. The definition of entropy is heat divided by temperature. At a constant pressure, the heat would be the delta H of the transition. So I get the following. The integral of the change in enthalpy of transition over T dt is equal to the integral of the change in volume of the transition dP. This is known as the Clapeyron equation, and it controls all phase equilibrium. It might not seem familiar now, but at the end of the day, the study of thermodynamics is the study of the background of all of the relationships that you may have learned in general chemistry. So each of these relationships will eventually begin to look familiar. You notice the transition is a function of temperature and of pressure. What happens? Two familiar phase transitions. Let's say I'm going from a liquid to a solid. The delta H is now the delta H of fusion. The delta V is now the delta V of fusion. The integral of 1 over T dt, I get the delta H of fusion log T2 over T1 is equal to the change in volume, the volume of the solid over the volume of the liquid, times P2 minus P1, where the volume in this case with the tilde over it is what is known as the molar volume. It's the volume of 1 mole of a compound or a substance given in cubic meters. The other familiar transition, going from liquid to gas. You now have the heat of vaporization and the change in volume of vaporization. This time, for the first time, we're going to make an estimate. By definition, delta V is final minus initial, so it's the volume of the gas minus the volume of the liquid. However, volume of a gas follows PV equals nRT. Volume of a liquid is simply equal to the density. 1 mole of liquid water has a volume of 18 milliliters. 1 mole of steam has a volume of 24 liters. So essentially, the difference between the volume of a gas and the same amount of material in the liquid phase is going to be the volume of the gas. So I get the integral of the heat of vaporization over T dt is equal to the volume of the gas dP. Since volume is not a native variable, substitute for the ideal gas law, and I get delta H over R, 1 over T squared dt is 1 over P dP. Do the integrals. 1 over P dP is log of P2 over P1. 1 over T squared is 1 over T1 minus 1 over T2. And as promised, if you remember your general chemistry, you get what should look familiar. You get the Clausius-Clapeyron equation. For the liquid-gas phase equilibrium, the Clapeyron equation comes down to log of P2 over P1 is the heat of vaporization over R, 1 over T1 minus 1 over T2. The Clapeyron equation also leads to something called the Ehrenfest classification of phase transitions. I can have what's called a first-order phase transition. This is called first order because the first derivative of entropy with respect to temperature at a constant pressure and volume with respect to pressure at a constant T are discontinuous. Discontinuity means if I plot either entropy versus temperature or volume versus pressure, I wind up with a line that has a gap in it. That gap represents a delta S for the transition or a delta V of the transition. The second Ehrenfest classification, second-order transitions, are continuous in the first order. Therefore, there's no change in entropy or volume, but there's a discontinuity in the second-order plot. The second derivative of entropy with respect to temperature is the heat capacity. So essentially, something that has a first-order transition has a change in volume and a change in entropy at the transition. Those would be transitions such as freezing or boiling. A second-order type of transition has no change in entropy or volume, but it does have a change in heat capacity. Those would be semiconducting transitions or superconducting transitions. If you've had your computer overheat, computers work on semiconductors that know only 1 and 0, where 1 is a conducting phase, 0 is a non-conducting phase or an insulating phase. Those two phases have two different heat capacities, so that if the computer gets too hot, you lose all the information. Essentially, the Ehrenfest classifications are useful and interesting because they define why we still study thermodynamics. Anything that was a first-order phase that involved a change of volume or a change in heat, with things like boiling, was the power behind the Industrial Revolution. Second-order phase transitions that involve semiconductors and superconductors are the basis of the information age. You look further at the fact that delta S of the transition dt is equal to delta V of the transition dp, the Clapeyron equation. You'll find that this arises from the second law of thermodynamics. dqp minus dq reversible is the definition of dg. Minus sdt plus vdp is equal to dg. So you get the delta S dt is equal to vdp. This is why the Clausius-Clapeyron equation, the Arrhenius-type relationship, log of y versus 1 over x, is so common in nature because it comes from the second law. Second law of thermodynamics basically says that if delta G is less than 0, a process must occur. If it's greater than 0, that process can never occur in the universe. And if it's equal to 0, you're at a steady state and you're at equilibrium. This governs not just chemical processes or questions in physical chemistry, it covers all processes in the universe, including biological or nuclear processes. Okay. Following video, we'll go into phase transitions in greater detail and is linked below. Thank you, and I hope you have found this useful.